So, shall we get started? I'm supposed to cancel. Okay. Welcome to the COCHE Seminar Series 28. So the topic of this seminar is about a flexible energy and sensing device. So in fact, today we have the topic focused on flexible sensing devices. It's mainly the members are from Professor Chunyi's group at COCHE. So next time it should be April, the end of April. That will be my group on flexible energy storage devices. So let's welcome the first speaker, Dr. Liang. His topic will be flexible ultrasonic sensor array for monitoring blood pressure. Dr. Liang, please.
Okay. Can you hear me?
Sure, clearly.
Okay. I will share my screen. Okay. Can you see my screen now?
Yeah, clearly. Make it full screen, please.
Okay. Hello, everyone. My name is Liang Ma, and my supervisor is Professor Chunyi. I'm glad that I have the opportunity to share my research work today. The topic of my research is the flexible ultrasonic sensor for monitoring blood pressure. Here is the outline of my report. First, let's briefly introduce the background. As we know that the cardiovascular disease are the leading cause of death globally, as recorded of World Health Organization. About 18 million people died from cardiovascular disease, representing more than 30% of all global deaths. The hypertension, also known as high blood pressure, is the most significant risk factor for cardiovascular disease. Therefore, it's essential to monitor the blood pressure for the early diagnosis and treatment of the CVDs. And now there are many methods for measurement the blood pressure. The gold standard of recording blood pressure is the cardiac catheterization. It is an invasive BP measurement method. So it will cause the patient suffering and increase the risk of infection. There are also many non-invasive blood pressure monitoring methods, such as the PPG sensor, pressure sensor, and the ultrasonic sensor. Compared with the other two kinds of methods, the ultrasound sensor has the advantage of the large detection depth. It can usually reach several centimeters. And the ultrasonic sensor needs no supporting structure, and it can measure the diameter of the vessel directly. So we choose this kind of method to monitoring the blood pressure. And now there are many ultrasound sensor for the for the monitoring of the biological signal of the CVDs. However, the traditional commercial ultrasound probe are usually heavy, rigid, and bulky, which is not suitable for long-term continuous and on-time monitoring of the blood pressure. To overcome these problems, we would like to develop a flexible ultrasound sensor. The sensor should be flexible and stretchable enough so that it can be attached on human skin for the long-term monitoring of the blood pressure. This part is the structural design of the flexible sensor. An island An island bridge layout with serpentine electrode is used in the flexible ultrasound sensor so that it can ensure that the device to be flexible and stretchable. The sensor array contains 2x4 transducers, and the size of each transducer is 1 by 1 millimeter, and the pitch is 1.6 millimeter. The thickness of the transducer is 0.3 millimeter, and the resonant frequency is about 5 megahertz. This picture shows the work principle of the ultrasonic sensor. The ultrasound sensor is designed as a array type, aims to mapping the vessel position, which enable to sensing and monitoring by a sensor overlaying the targeted vessel without manual positioning. Each transducer can individually generate and receive ultrasound wave. When the ultrasonic wave reaches the interface between the tissue and the vessel, both transmission and reflection occur. The reflection wave carries critical location information about the interface. At both the front and back interface, the ultrasonic wave will reflect. Therefore, the vessel diameter can be calculated by the time difference of the received signals. And then we can get the blood pressure as the following equation. If we want to get a more accuracy result, we can use smaller size transducers. This slide shows the fabrication process. Here, multi-step transfer printing are used to integrate the top and bottom electrodes. The total size of the sensor array is 20 by 25 millimeter, and the thickness is less than 0.4 millimeter. The weight of the device is less than 0.3 gram. The entire device is encapsulated with silicon rubber to ensure it to be flexible and stretchable so that it can be attached on the skin. In order to simplify the fabrication process, a vertical axis is used to make the two-layer electrode to be the one layer electrode. This method also can give a larger space for the integration with other sensors. In addition, the stamp-based transprinting is used to replace the traditional model-based assembly. So, bulky transfer of all the 8 transducers can realize by using the PDMS stamp. The resonant frequency is a key parameter of ultrasonic sensor. The traditional PCT transducer usually has 2 vibration modes, which are the transverse vibration and the vertical vibration. Due to the thickness is usually smaller than the side length, so the transverse vibration is located as the low frequency band, so that the traditional PCT transducer has a lower resonant frequency. It is not suitable for the high resolution measurement. For the 1-3 composite transducer, the transverse vibration is suppressed and only vertical vibration can be occur. So that the 1-3 composite transducer has a larger resonant frequency. Therefore, we choose this kind of material as the flexible ultrasonic sensor. Here are the resonant frequency test results of the 8 transducers. The mean resonant frequency is 5.37 megahertz, and the anti-resonant frequency is 5.34 megahertz. The standard deviation is about 43 kilohertz and 70 kilohertz. The coupling coefficient is about 0.54. Here is the echo test result. From the result, we can see that there is a distinct echo signal. After FFT, we can get the further plots. It shows that the resonant frequency is 5.08 megahertz. The material of the electrode can also affect the performance of the ultrasonic sensor. Here we test 2 different kinds of electrode. First, the polyimide and copper electrode. And the copper electrode, the thickness of the copper electrode is 10 micrometer. From the result, we can know that the ultrasonic transducer with polyimide copper electrode has a large output voltage. This is because the ultrasonic wave will reflect at the interface between the transducer and the electrode. Since the polyimide has a lower acoustic impedance, so that we choose the PI, the polyimide copper electrode, as the in the design of the ultrasonic transducer. Here is we also use the fabricated ultrasonic sensor to measure the diameter. The sensor array is attached on the arm. From the result, we can see that there are 2 peaks, and the peak will shift as the diameter change. It should note that the arterial wall and the echo signal of the arterial wall and the posterior wall is different. This is because the ultrasonic sensor is flexible and has a lightweight, so that there is a little pressure on the artery, so that the movement of the artery is not affected by the ultrasonic sensor. This will cause the movement difference. From the echo signal, we can know that the diameter of the vessel varies between 5.11 millimeter and 5.32 millimeter, and the waveform is consistent with the blood pressure waveform, and the spatial resolution is 1.32 micrometer, and the temporal resolution is 1 millisecond. Here is the conclusion. A flexible ultrasonic sensor array is designed, and bulky transfer printing is used to fabricate the sensor array. The performance of the sensor is tested, and the resonant frequency is about 5 megahertz. The diameter of the artery is measured by using the designed ultrasonic sensor. And next step, we will integrate with pulse waveform velocity sensor with the ultrasonic sensor for the pulse wave velocity sensor. Mr. Zhang Zhou will introduce later, and then we will calculate the ultrasonic sensor for more accuracy BP measurement. Okay, that's all my presentations. Thanks for your listening.
Okay, thank you very much. Any questions from audience? I got a question about the power requirements for your sensors.
Pardon?
Power requirements, for example, the voltage you use.
Voltage, the voltage is 200 watt.
200 watts.
Yes. From here we can see the voltage is.
Plus you
But it is pulse. It's a pulse. The pulse width is 100 nanosecond. The power is about several million joule. Several micro joule.
okay.
Yeah.
So in this case, do you use battery to power or just use outlet to connect, or how do you
battery?
Use battery, right?
And now we use the pulse receiver, and we can also use battery, but the circuit should be enough to generate the high volt pulse. Yeah.
Okay.
Chunyi, I just want to comment. I think Dr. Zhi asked a very valid question. I think it's a good time now to actually investigate what could be the suitable step-up circuit for the wearable setting. I mean, the first step is, of course, you can use the power generator to provide the high voltage. But once you want to implement everything in the wearable platform, then I mean, we will for sure use battery to drive it, and then you would need a step up circuit to step up the 10 volt to a few hundred volts. I mean, this is a very common function, but still, if you don't show people the solution, and it's hard to convince people that it could be eventually implemented in a wearable form. I mean, there are already a lot of off-the-shelf available solutions, but I think it's good to I mean, purchased a few possible kits to demonstrate it can be done in a wearable setting. Yeah.
Okay.
Okay, later maybe we arrange a meeting to discuss how to integrate your sensors with batteries.
With battery, yeah.
Yeah, we can
that
provide
would be very interesting
solution together.
Yeah.
So. Any other questions from audience?
Yeah, I just wondered that, Chunyi, thank you for your wonderful job. I just wonder, how do you further improve the spatial and the temporal resolution? It seems to me it's already very good. 1.3 micrometer. What effect is? How do you improve the resolution further?
I think the backing layer I want to use to make the bandwidth wider than this one. The backing layer I want to use here, and the other method to increase the accuracy is to make the pitch smaller, so that we could measure the diameter more accuracy, I think.
Thank you.
The pitch now is 1.6 millimeter, and I think we can fabricate a sensor with smaller pitch.
Any other questions?
Can I ask questions?
Okay.
Oh, so hello, Dr. Liang, and thank you so much for your wonderful presentation. And I have a question about the pitch as well. So since the pitch actually is several times larger than your wavelength, so how do you deal with the grating lobes of your sound? I mean, did you apply some filters or did you do some focusing design?
Oh, I know. For the imaging and demo imaging, the pitch should be the half wavelength. But but for the measurement of the artery, we use A mode, so that we don't need to make the pitch to that small.
Okay, thank you so much.
Okay.
So any other questions? Okay, if not, we stop here. Thank you, Dr. Liang. So
Okay, thank you.
The next speaker is Mr. Zhou. He's a PhD student. His topic will be about flexible pressure sensor array for PWV monitoring. So please.
Hello, can you, did I just share my screen?
We're
Can you see the screen?
We're waiting for that.
With my computer has just got some problem.
And would you also switch on your video?
Oh, sure.
Please. Yeah, video on, please. Yeah, okay, good. Go ahead to present.
Okay. Good afternoon, everyone. I am Jiang Zhou, a PhD student from City University Biomedical Engineering Department, and I'm a group member of Professor Zhang and Professor Zhao. It's my great honor to be here in the seminar and give a short presentation about my work. Today my topic is flexible pressure sensor array for pulse wave velocity monitoring in cardiovascular disease detection. So first, I still want to make a short introduction for cardiovascular disease. As it was widely acknowledged, cardiovascular disease are the leading cause of death globally, taking an estimated 18 million lives each year. So cardiovascular disease are characterized by its high morbidity and mortality rates, and the timeliness of treatment is much higher than any other of diseases. So this makes the prevention and early detection of cardiovascular disease of great significance. So right now, there are mainly three types of tests for cardiovascular general cardiovascular disease: general physical testing, blood testing, and invasive testing. But for the early detection of and prevention, I think the non-invasive general physical testing is the best option, as it is suitable for all kinds of people, regardless of current symptoms. Visually, this kind of tests should be completed with devices such as blood pressure device, pulse wave velocity device, or heart rate, etc. So today I would like to introduce my pulse wave velocity sensor arrays. But first of all, what is pulse wave velocity? So the traditional pulse wave velocity refers to regional PWV. It is a well-established surrogate marker of atrial stiffness, and it estimates over different atrial trajectory. Is known to provide information on vascular structural dynamics, events relating to end organ damage, transmural pressure exerted on the arterial walls, and the influence of biological aging on atrial stiffness, even at the cellular level. So the estimates of regional PWV are therefore treated as therapeutic targets in various vascular and hypertensive heart disease. So there has also been tremendous technological advances in regional PWV-based approaches for cuffless evaluation of atrial blood pressure parameters. The right picture shows the established technologies for regional PWV measurement over the arterial tree. And the widely used approach is based on the acquisition of blood pulse waveforms from two different superficial arteries where the position can be easily felt. Following the fundamental distance-time relationship, the time taken by blood pulse to travel between the recording sites is divided into arterial trajectory lengths to obtain the regional PWV. The most widely used is carotid to femoral PWV. However, while the carotid or to femoral PWV remains the like a golden standard is estimate of arterial stiffness, research developments supported by advancing technologies has generated considerable interest in measurement of local PWV. However, in recent decades, as local PWV began to gain increasing levels of interest because of the superiority in its distinctive features over those conventional regional PWV. When compared to regional PWV, measurement errors associated with the determination of like blood pulse propagation distance, modifications in the fissuring shape of pulse waveforms acquired from different arterial sites, and the effect multiple arterial wave reflections in local PWV estimates are minimal. So this justification is straightforward. All the measurements are being performed locally over a small section from like single size of the target artery. So therefore, unlike the average estimates over the regional PWV, the local PWV provides an estimate close to true propagation speed of blood pulse waves through a specific artery. The function properties of individual arteries and the specific artery segments can be evaluated with the local evaluation of PWV and its variation over time. Recent studies has demonstrated that the local PWV is precisely related to vascular characteristics, biomechanical information, transmural blood pressure level, and the patient's physiology of artery under investigation. So now local PWV is clinically significant and is being used as an indicator of vascular damage and is a like potential risk factor of coronary heart disease and stroke. Emerging evidence from various clinical studies has now established that the local PWV measured from carotid artery is robust surrogate marker of virus cardiovascular disease. So further, the vascular pathologies of the central artery system can be investigated using local PWV obtained from aorta to carotid artery. So as the medical measurement technologies have advanced, non-invasive assessment of local PWV pulse wave velocity has been of much more meaningful than ever. So there are several types of ways to measure the local PWV, including like hemodynamic loop-based approach, dual site measurement, and like multi-site measurement. Here we choose to use pressure sensor array to measure the pulse signal. A pressure sensor array is measure the pressure change in blood vessel caused by a pulse wave. Here we use PVDF. This is a polymer piezoelectric material to fabricate the pressure sensor with the Allen bridge structure and encapsulated with EcoFlex to maintain its flexibility and stretchability. First, we did some simulations for the PVDF pressure sensor. First, we tried the just the PVDF sensor with uniform force. And we found that compared to another simulation, which is PVDF sensor with PI layer, we found that with the supporting layer, we can get a better signal. Also, we did a simulation to compare with the sensor field with EcoFlex and PDMS. And we found the PVDF sensor filled with EcoFlex gets a better signal. So here is a very simple. This is a very simple table. Very simple for our simulation results. Also, with the capacity of PDMS, we can also get a better signal. That is also overall. That is why we decided to choose using PI as a supporting layer and capsulate with EcoFlex to fabricate our sensor arrays. So here are some of the data we acquired from Verizon Laboratory. This is a small prototype of we made for some just for some little testing, and these are several very complete pulse wave cycles tests from our device, and we can see there's a little bit shift right for the second pulse wave. The pulse transit time vary from 3.2 millisecond to 5.2 millisecond. The distance between two pressure sensors is 20 millimeters. Then we can get the pulse wave velocity is around like 47 meters per second. Also, for local PWV, the maximum of the pulse wave cycle is easily affected by the noise of data collection system and the propagation of reflected lateral pressure waves. So that is why if the signal to noise ratio is not very good, the maximum of pulse wave cycle is generally not considered as a reliable critical point. So here we use the maximum of first derivative data to calculate the PWV. This is a point on the original pulse circle where its slope going into a systolic pressure reaches a maximum. So from this data, the pulse transit time is between 1.2 millisecond to 4.5 milliseconds. So we can get the pulse wave velocity is around 4 to 8 meters per second. So here is a table. Here's a table of local PWV from different places of human body. From this data, we can get just from this data we can see that our pulse wave velocity test result is pretty it's okay. And the right picture is a characterization for our device. We use a 30 millimeter PI as a supporting layer, and this shows that our device has a very nice response for the linear pressure force. So for the next step, the first is we need to test the local PWV from different locations of human body, and also optimize the PWV sensor with PDMS cavity and compare different thickness of supporting layer. And then we will try to integrate the PWV sensor with other sensors like what Dr. Liang just said, the ultrasound sensor. So this is all my presentation, and thanks everybody. Thanks for listening. Thanks.
Okay, thanks, Joe. And so now we have some time for questions. Any questions from the audience?
Sorry, may I ask a question?
Excuse me?
Hello?
May I ask a question?
Oh, sure, go ahead.
Sorry, there was a bit disconnection. I couldn't follow. I wanted to ask if you checked your results with the existing methods to measure the pulse velocity or not, because I know SFigma Core and compiler does that.
I didn't get it. Excuse me, could you repeat your question?
Actually, there are devices which measure pulse wave velocity already.
Oh, yeah, right.
Yeah. I wanted to ask if you have made any comparison with them or not.
Yeah, we actually are testing our PWV with different structures, like different cavities, different supporting layers, and finally, we need to integrate our device with other sensors.
No, the question is, there are some standard devices that people use in the hospital, for instance, to measure PWV, not local PWV, but the general, the PWV along arterial trees. So the question was, have you tried to compare your PWV measurement with the ones done in a more sort of conventional way, using standard systems?
We haven't tried the conventional way, which is regional PWV. We just did the local PRV test, and we compared that data with some other assets, but we haven't compared that with the hospital golden standard device.
Yeah, I think that's something to think about. What are people I mean, you're measuring local PWV, so which might slightly be different from the standard practice.
Yes,
but even for local PWV, there should also be ways of checking whether the values you measure make sense or not. Currently, all what we can see is that the value falls in sort of a reasonable data range, but we don't know how precise it is, right? So
yes,
I think sooner or later that would be something to check.
Yeah. Because PWV varies from people to people and places. to places.
Yes. So you still need a calibration device.
Yeah, indeed.
Yeah, also there are techniques to kind of because, for example, when you measure, you can actually for different different pulse rates of heart, you can collect data, and somehow you can combine this data or fuse several data to increase your resolution and improve your data. So I have heard that there are techniques to for data fusion or something that improve the measurement of pulse wave velocity based on these signal processing techniques. So there are room for research on that also, I think.
Yeah,
Thank you.
Thank you for your suggestion.
Any other questions? If no, thanks, Joe. I think we will move to the next presentation. The title of the next presentation is Super Flexible Metal Bioelectrode Ensuring Comfort Wearing, aiming to, that's a rather long title, aiming to develop sensing system for the control of CVD. Dr. Shuaicheng Wang will be giving the talk. So Shuaicheng, you can start whenever you're ready.
Yes, thank you very much. I'm very happy to have a chance to introduce my work to so many experts here. My work is based on the developed on the basis of a technique called polymer assisted metal deposition technology, and it's a very powerful new technology to generate thin film metal electrodes on the varieties of substrates, and such as biological tissues such as flowers or bacteria, and can grow a very nano-sized metal thin film on the surface of the substrate in the room temperature and in the very normal conditions with no very serious conditions. So I will introduce a little bit about my little work. I developed this kind of this is the first papers I tried to publish in the COCHE Center, and it's I developed of this polymer assisted metal deposition technology. It can be used to deposit thin film, very durable thin film metals on the plastic substrate, and very durable, can be embedded on the clothes for energy generation, and so after testing, they can be very durable and they can easily pass the pull-off test, and with very strong force, it will not get off. So it's a very powerful way to deposit thin film metal electrodes, and then I will my purpose is to develop this kind of metal electrodes on to fabricate a new generation of ECG sensors. The currently commercialized ECG sensors have a thick iron core and wires, very thick wires. And the first problem is that they are very wasted. They consume a lot. After one time test, they will waste around 10 electrodes and throw it away. So it's an everyday so it's a very big market, and it's thanks for the market design by the Miss Jiuru Du, 然后thank you for her help to develop the market, research the market, and show that they have the potential target market of around 0.23 billion US dollar, and in the 2024 it will reach to more than 1 billion US dollar, and in the people to also in the hospital and high-end clinical, and it will bring unprecedented experience to patients. And the second problem of current commercialized ECG sensors is that very not comfortable to wear, and it even I choose the best original electrodes from the company of Lepu Medical, and it's very expensive electrodes, but it also will cause the skin allergies and reddish redness because they are not breathable. They are very thick, and after attaching for 1 day, and it will have lots of redness, and even after 5 days, it still continues have. And it's very harmful for the body, especially and this kind of electrode also on the market is in another big company is called Biopack, and this kind of device, this kind of ECG sensors is even more harmful for the body because after they have some very rigid skeletons, plastic skeletons in the center, and lots of gels in the center, and it will just because of the existence of the rigid skeletons, it will make the skin very harmful, very have allergies. It's in my arm, it's after 8 days, it still have some redness, so it's not a good way. And another kind of problem is that the sports is also cannot work because ECG detection have to have 24 hours, and if people work, if people exercise, maybe we'll have some sweat, and sweat will weaken the attention, and in addition the wires is very heavy. And if we jump, and it will just get off from the skin. So it's I have a video, but maybe cannot play. Okay, I'm sorry, maybe a problem on my computer. Okay, so my purpose is to fabricate lightweight or extremely lightweight ECG sensors for the people to detect it, not lie on the bed, not in the hospital, just work as normal, and make it very lightweight and cannot get off when after exercise and use. So we successfully fabricated this kind of electrodes and tried it on the body, and this mode is successful and easy to work. And now we established the detection system. This detection system, thanks for Miss Jessica, and she operate this Biopack ECG sensors very well, and now we developed a system to compare ECG sensors, and they can be used to compare varieties of these newly prepared ECG sensors. And originally we should buy 2 wires, and I made one, so make it perfectly can work well to compare varieties of this system can establish very well, and can be used to compare the ECG sensors from different ECG signals from different ECG sensors. So we compared first the electrodes from this is one used, and this is non-used, and they can have they are all from the big company, and the first two is original data, and the second 2 is after the filter. So we first compared the originally very good use this system to compare the electrode ECG sensors from the 2 big companies in the market, and first with Biopack, and this is very harmful for skin, I think. And this is a big type of ECG sensors, and they can be used only once. After one time use, it will dry immediately. And but they have the best signals. They have the best accuracy, and this is another kind of major ECG sensors in the market, and they have a very good gel structure, and this gel structure will not dry, and it can reuse many times. And this is a new one, and I want to compare this two electrodes in the new one and compare it. For after comparison, the original data in the 5 and 13 channel is we can find that their resolution is all very good, and after the filter addition, and they can be also almost similar, and so it demonstrates that the new one is of these two electrodes are all very good to use. And and because the second one, the gel, is can use many times, I tried to demonstrate it detect it for 1 day, and then the next day I will use it again, reuse it again. We can find that the signals is not good as before, and especially in real data in comparison with the first one. I use this as a comparatives group, and I use it as a new one, and this one is a reused one. Reused one will make a noise, lots of noise, but after filter they performed also very well. So it shows that our system can detect the signals very well. So now this is my I prepared electrodes, thin film electrodes, very flexible, and this is detect on the skin, and we compared with original the best BioPack ECG sensors, and we found that the signals we generated are almost the same, not almost, exactly the same. The accuracy is similar, and we fabricated the flexible, ultra flexible one, and with the silver chloride in the surface, and with the gel in the surface, with the help of silver chloride and with the help of gel, they can be very almost the same as the commercial one. Actually, they are the same, and even better, even similar level with the other gel one. And so this is a detection process video. I don't know why I cannot play. So I also tested if we get rid of the silver chloride or get rid of gel, can that work? Can that pure silver electrode work? We can find out the flexible silver electrodes is here, and we can find out the gel the signals is not accurate as before, and it's almost no signals. But after filter, it can get some signals, pulse signals, but it cannot work obviously. And so so then we added the silver chloride, but didn't added the gel, and I want to find the difference. After the addition of the silver chloride, we can find that wow, these signals become better now. And originally they don't have the accurate signal, but after the addition of silver chloride and after filter, and they can get almost the similar level of similar good results as a commercial one, the best commercial one. And this is with no gel in between the skin and the electrode, so it can use for extremely long time. So after filter, we can get a clear message. But after the addition of the gel, we can get the similar result as a commercialized electrodes. It's almost the same. It is the same. So this mode of technology is potential to be applied to the large production, and this is the demonstration of the existence of the silver chloride. This silver chloride was marked as red, and the green one is a silver peak. We can find that after treatment they have a very precise silver chloride electrode, and we can make it very smooth. and but they are not brassable. They are so we can also make some holes on the surface of it and make it brassable. And after making some holes on the surface of it, it still have a very clear silver chloride electrodes, and with silver in the gray and silver chloride in the red. So it's applicable. And then the next type is to demonstrate, to carry out the Bell cytotoxicity test, and I collaborate with Dr. Li Jingkang, and we did a little work, and this is we show that the the cells can grow on the surface, shows very good compatibility. We'll note that. And in the future, we will continue do all the things, all this biological cytotoxicity test to the silver electrode and silver chloride electrodes, and without the gel. We want to further show this one. And this is equipment that arrived 2 weeks ago, and I just need time to use this impedance analyzer to carry out the skin electrode impedance. I want to show the difference between the commercialized one and our electrodes. We can find that we can do the similar work as this one did, and they can show. I'm assuming that we can be similar with a commercialized one. So and finally we have to deal with the recycling of the waste. I also did some attemptory research on the detecting the material of the component of the material waste, and I want to reduce the waste. After reduce the waste, I can make the project very complete, and this is a major plan and a major business style. And thank you so much for your listening. And I will thank you so much for my supervisor, Professor Zhao Ni, and give me great advices and help. And thanks for all the members in COCHE and Professor Zhang's give me great support. And thank you for my group members. And thank you so much. And now I will open my board and waiting for your comments and advices. Thank you so much.
Thank you, Shuai Chen. Now the time is for questions. Any questions from the audience? Maybe I can get started. Shuai Chen, you showed the figure at the very beginning that after you weld the commercial electrodes for a while, we can certainly see a lot of red spots developed on your body. Have you tested the performance or the skin reaction to your electrode? Supposedly it is it is grown on a breathable substrate like breathable bandage or porous substrate, but then your film is a continuous film. So how is your skin react to the new electrode? Can you comment?
Yes. The biggest difference between our electrodes and their electrodes is the thickness of the substrate. Our substrate is very thin, and it's a polymer membrane, and they are porous. Actually, the water molecule will evaporate and penetrate.
Yeah, I understand your substrate is porous and the water can go through, but the water still has to go through your electrode, right? Which is a continuous film.
Yes, I can try to make the continuous film to a porous one, and after they have some porous structures, they can be theoretically they can be more brassable and give the skin less damage and make it more comfortable.
Can you maybe even just is it possible at all to not deliberately make it porous, but just to create some holes, maybe with laser cut or whatever on the electrode, so that the water can sort of evaporate away from the, I mean, for instance, for this figure, can you just dig 4 holes? Just introduce some holes. I mean, not damage the film. Because I saw on the next page, when you deliberately introduce a lot of pores, you may sacrifice the film quality. But what I was wondering is, can you pattern some holes some non-destructive method, so that your film, the remaining of the film will still have a high quality.
Yes, I think this is a yes, this is a practical solution. Yes, we have and we have the laser, very accurate laser, ultraviolet laser with a radius of 15 micrometer, and but I think the only problem is that the micrometer size is a little bit large, and so this porous is around 20 nanometer. It should be nanometer. Yes, it should be nanometer. So it should belongs to the mesoporous structure. So maybe this one its porous size is little, and so this one. So maybe if we use a laser, the smallest size in our now the highest level is 15 micrometer. So maybe it's a little too large, and so this is the reason that I want to use this small size and porous. I think making it better. I think better looking. Yes, I may try to fabricate larger size the ECG sensors and to have the larger size the holes to try. Yes, for the skin reddish or redness or skin allergy detection in different samples. Yes, I think it's a good way to solve this problem and make the picture more convincing. Yes.
Okay, thank you. I'll leave some time for other questions if the audience has any other questions.
Well, thank you, Shuicheng and Li, for your wonderful job. I just wonder that you know, your research work is very practical. You know, have potential big application. Do you have any plan to apply ideation?
Apply ideation.
Science Park have some support, help you to start up. And I think that money is not big.
I want to
but the experience, you know, some kind of interaction would help you, you know, learn something different from academic work.
Yes. Yes, thank you for advice. I may concentrate in ideological thing. Yes.
You may talk to you know, Solina and other people who already got it. It's not that complicated, but I think you may want to try to catch the next deadline. Yeah.
Yes, I'm trying to apply it for it. Yes.
Thank you, Shuicheng.
Yeah, thank you.
Okay, thank you, Professor Zhang. Any other questions or comments? If not, let's thank Shuicheng again, and we move to the last presentation today. The last speaker is Mr. Zhao Lei, and today he is going to give a presentation on information fusion for long-term and continuous blood pressure monitoring. Lei, are you there? All right, so you can start whenever you are ready.
Okay, can you hear me?
Yes.
Professor? Okay.
Yes, I can hear you.
Okay, I will switch to the full screen mode. Thank you all. And my presentation title is Information Fusion for Long-Term and Continuous Blood Pressure Monitoring. And my name is Lei Zhao, and my supervisors are Professor Ni Zhao and Professor Yuanting Zhang. Here are the contents of this presentation. In daily life, we will wear a watch-like thing. For example, we will perhaps wear an Apple Watch or some other brands smartwatch. And in practice, it is very common to find that the contact between the watch and our skin will vary in some situations. For example, here we discuss two main factors. The first is hand posture. If we put our hand in a flat posture, and the watch will contact to the skin tightly. And in contrast, if we put our hand into the erect posture, and it will be loose. And in some situations, we will manually we will manually change the tightness. For example, we will make the belt short or long to make us feel more comfortable. All these behaviors will change the contact condition between the sensors and our skin. And academically, we could see from the figure 2. Here are the total equivalent elastic strain simulation of the sensor skin inter effects. We could see from the lower panel, when the contact changes, the blood vessel diameter will also change, and this will finally change the blood volume inside the blood vessel.
Harley, are you changing your slides or you stay on the same slides?
No, it's still on the first slide.
Oh, okay, thank you.
Yeah. Okay, can you see the video?
Yes, we can see the simulation.
Oh, okay, that's good. So here, what I want to say is, the contact between the sensor and skin will change our sensor's response, and finally, this will affect the model's prediction. So, and my focus is on this problem. To solve this problem, there are already some good works. For example, these 2 works are published on the IEEE TBME. In figure 3, Dr. Xiaofei Tan proposed this PV model to express the relation between the blood volume and the transmural pressure. This is a sigmoid-like curve, but it is not indeed sigmoid because it is asymmetric. And we could see this also from the lower panel. This is a corresponding compliance curve. And she applied this PV curve into the PDT model. And finally, she found that if we take this factor into consideration, we will get a good improvement in the blood pressure estimation. So it is valuable to consider this factor. Also, in the figure 4, this is another work. The author tried to calculate the PAT in under the different contact pressure, and yes, we finally got a varying PAT on the different contact pressure. We could see in the first 2 pictures. For example, in this green curve, when CP gets larger, the PAT will get lower, and it is almost linear. So it's useful to consider these problems, and to solve this problem, I proposed myself a solution. Here shows a paradigm of the method. First, in the inference phase, this model will be separated into 3 parts. That is a conversion model, scaling model, and a fine transformation. The conversion model will convert the raw PPG signal into another domain. And in that domain, this PPG signal is actually like a pressure value. It is not the intensity of optical signal. It is be transformed into another meaning. And we do the scaling to the TAG. So finally, they will be in the same domain, and we can do the summation to them. And finally, do some affine operations, we could get a BP estimate. And to train this model, it is very simple. We could use a BP reference we got from some standard, a golden standard. For example, we could use a CNAP continuous BP monitor, or use oscillometric ways to get the BP reference. And we use this BP reference to tune the parameters or coefficients in these submodels. And finally, after these parameters are all tuned, we could use them to predict blood pressure. And to test its performance, I designed and conducted some experiments. And the experiment can be divided into two parts. First is for continuous BP, or CBP, and the other part is long-term BP, LTBP. To test the continuous BP monitoring performance, for each subject, we extract two sets of data. That is the training data and the evaluation data. The training data has two sequences. The first is with a very broad range of TAG amplitude, and the another sequence is just for a fine transformation tuning. So in the training phase, we use training data, the first sequence, to fit a surface of BP, TAG, and PPG. And from this equation, we could solve the BP equation. Here we could see the TAG prime and the PPG prime. They are all transformed or scaled from the raw domain to the target domain. And then we use the tune data, or the second sequence in the training data, to tune the scale factor U. And in the testing phase, we use data to calibrate, to only calibrate the shift coefficient V. So finally, this model is ready for later monitoring, either in the continuous way or long-term way. And for long-term BP, here we designed a protocol. We actually monitored each subject for about a half month, and each test will be conducted just after 1 day or 2 days after the last test or tune. So overall, we could have 7 days of data, and we use this data to measure. We use the data to measure the long-term BP monitoring performance. And for each data collection, we have these 5 steps to do the data extraction. So the result is here. For CBP monitoring, I selected just one subject, and this figure shows DBP tracking, because if I put more data here, that will make this slide looks messy. So I don't want to put too much. The upper panel shows the proposed model vs the reference value, and the lower panel shows the PDD model and the reference value. So it is obvious that the proposed model can track much detail than the PDD model. Actually, PDD model could also track the change, but that is too rough. For example, in the first 100 cycles, the blood pressure is increasing overall, and the PDT is also increasing. And in the last part of this sequence, the pressure is going down, and so does the PDT model. But if we zoom in, we could see much details in the proposed model prediction. Yeah. And for each subject, here we have 24 subjects up to now. And I will do more clinical trials with the help from Jessica, and we will do more clinical trials in hospital to collect more data to validate this model. This table shows the BP monitoring performance for each subject. And I select MAE, mean absolute error, and root mean squared error as a metrics to evaluate the model. So you could say either for MAE or MCE, and both DBP and SBP, the proposed model could do the best work overall. Yeah, perhaps at some cases, the PDT could reach the best result. But overall, the proposed model is the best, and we could also see these consequence in these figures and tables. Actually, these figures and tables are the same. We could see in the MAE and RMC comparison, the proposed model is always the best in all situations. And the tightness comparison is also done for these models. By the way, I use a static baseline. That is a mean value of the calibration data. So if we could infer the BP with just a mean value, then if your model cannot outperform that mean value, then it is obvious not good. So here I selected the static baseline as a model here, and obviously the PDT model and the proposed model are all better than the static model. And for the LTBP monitoring, here shows the trend of the tracking performance. Here the metric is MAE, and we could see in the first 4 days, this PDT or the proposed model are all good, and the MAE is under 10 millimeters of mercury, and after 5 days, and the situation will change. Perhaps the PDT for SBP will first get much larger error than the proposed model, and finally, at the 7th day, they are all not so good as they tuned at the first day. So here I proposed a model, of information fusion model, to make the best of the amplitude of these easily obtainable PPG and TAG signals for cavities and continuous BP monitoring. And we are extending this method to wearable device-based cavities BP monitoring because so far we are using the finger to do these experiments, but later I think we'd better to do the wearable device-based tests to show its potential application for more scenarios, and those next scenarios are very important for daily monitoring of our cardiovascular status. Yeah, and this method still suffers from some problems, such as sensitivity to the location and long-term recession, and we are trying to overcome these problems later. But now I think our first target should be focused on the wearable device. Yeah, and okay, that's all of my presentation. Thank you.
Thank you, Lei. Any questions from the audience?
Well, thank you, Lei, for your very interesting work. Can you go back to the long-term BP results? Yeah, here. The next one, yeah, this one. Do you have any clue how to fix the long-term BP estimation problem? It seems to me none of these perform up to the standard, right? At the first few days, okay, but it
Yes.
seems to me that after 5 days or 6 days, all of them are having very big error.
Yes.
Do you see what the problem could be potentially? How do you fix it? Do you have any thought on that or so far? I know this is a problem,
Yeah.
but
Yes, you're right. If we make this longer, then you could see a much larger error. Perhaps if we do this in a month, then we could get much error than this. And I think the reason cause this performance decay is because our body will change, and so does our blood vessels and our tissues. So if these tissues properties changed, then we will have a different situation for our model to predict BP. So it is a nature, and I don't think if we just based on the model itself, actually this is actually another topic that we need to consider more. But now what I focus on at this moment is the continuous accuracy, and so I just show the probability of this method to long-term tracking the blood pressure. So perhaps I will do it later, just after this project, to show to find out more solutions to track our BP in long term. Yeah, perhaps later.
right. So the some group, including our own group, Supun's work, he can using deep learning to track the BP change for longer term. I'm not quite sure. Did you try the same database for your method?
Actually, I don't know whether they used the TAG signal, because yeah, in many researches they use ECG and PPG. They are common, but TAG signal are always just be treated as a demonstration for device design. So I'm not sure we use the same data or the same modalities. Yeah.
Thank you.
Yeah, I think yeah, it is a problem for the long-term trackability. So I actually have a follow-up question related to Professor Zhang's question. So in your calibration, for BP calibration, did you see a huge impact on how you calibrate the data? Like, say, if you provide a few points for calibration, or if you provide multi-day measurement points for calibration, or if you use a BP with a large dynamic range for calibration, would that make a difference in long-term trackability? Because I assume if what you said is true, that our bodies change, and then if you include different scenarios during training, supposedly the prediction might be better, might have a better results. Whereas if you only have, let's say, a very short time calibration, like maybe calibration of BP, continuous BP for 10 seconds, or just a couple of scattering points you measured from oscillometric sort of devices, then it may not be able to reflect this change in your training phase, and then that may sort of limit the performance of your device for beyond 7-day or beyond 5-day prediction.
Yeah, actually, for calibration period or the calibration data points, in CBP tracking estimation, and I just use the first 100 cycles to calibrate, and this number n can also be tuned or changed. And I'm also thinking over to change this n to see the prediction performance later. Yeah. And for long-term BP, here we just tune the model as a first step. So it won't be changed. The coefficients or parameters won't be changed in the later tests. We won't let the model see these tests again. They see this test data again. So, perhaps this is also a reason that's why the long-term tracking performance will decay. Yeah, apart from the our body change or the location change, will also affect the long-term BP tracking, and the calibration period or the calibration length will also change it. So totally we have three reasons that's why long-term BP tracking performance will decay. Now we have three reasons, and later I'm not sure whether if we add more tune or more calibration. For example, if we do another calibration in the third day or somewhere, I'm not sure whether it will affect the model's capability of BP tracking. Perhaps yes, it should be positive.
I mean, even if you just do 1 point measurement, just with Omron,
yeah,
would that help somehow to sort of bring the results back to a more accurate level? I'm just curious, just to see how this could be addressed.
Yeah.
If short-term tracking appears to be good, are there some simple ways of addressing the long-term tracking performance or problems? Yeah.
Perhaps that will be helpful if we add more calibration. But so far, in this work, we just do it once, and also with the Omron oscillometric method. Yeah. And but the training is also with the continuous data because we need many data points to fit this surface. That is in demand. But I think you're right. If we add more calibration, the performance will be maintained each time we calibrate it. Yeah.
Yeah, thank you. Any other questions from the audience? All right, so today we had 4 presentations with 3 focusing on developing sensors. We had talks on ultrasound sensor, then pressure sensor, and then finally ECG sensor, and then we had the last talk focusing on the algorithm part. Now we still have some time for a general discussion on the topics today, and we still have all the presenters here. So if the audience would like to raise any questions for any of the previous talks, now is a good time to ask your questions, or any comments or any suggestions to the presenters. Please, you're very welcome to make your suggestions or comments. All right, seems we don't have